Auzubillahi Minash-Shaytanir-Rajim. Bismillahir-Rahmanir-Rahim. Today our topic is the basic concepts of Ecg. Now, as you know that Ecg is actually electrocardiogram, and this is a technique which records the electrical activities of the heart, which are initiated by the nodal cells of the myocardium. Now, today we will study the basic concepts, and inshallah in the next video we will study the advanced Ecg. So let's observe how the electrical impulses generate in the heart and how the electrical impulses spread over the myocardium and how it enables the contraction and relaxation of the heart. Let's study. Suppose this is a heart. Suppose this is heart. This is right atrium. This is left atrium. This is right ventricle, and this is left ventricle. This is a simple diagram of the heart. As we have already studied that actually impulses are generated by special types of the nodal cells, which are called the SA node, or we can say the sinoatrial node. So the sinoatrial node, which are located on the dorsal side, on the dorsal right side of the right ventricle, it actually generates the electrical impulses. So we can say this is what? This is SA node. This SA node, it will generate what? It will generate the electrical impulses, and after the generation of the electrical impulses, it will spread throughout the heart myocardium, or we can say the myocardial cells. So suppose we take a small piece from the heart. We can say this is a myocardium. Let's take a myocardial cells from the heart and let's observe the electrical activity in that myocardium, which are recorded by a special type of instrument called the galvanometer. Suppose the first observation. Suppose this is what? This is myocardial cell. This is what? Myocardial cells. As you know that myocardial tissues or cells are composed of small myocardial cells. This is what? This is small myocardial cells. And this myocardial cells is attached with a galvanometer to record all its electrical impulses or its electrical activities. Suppose this is A in, this is what? A in, and this is B in. Suppose this is the positive end of what? This is negative end. And this positive end is also attached into the galvanometer, and this negative end is also attached to the galvanometer in order to record the electrical activities of the heart. Now, this is what? There is a galvanometer. And there is a needle which is usually in the center at a zero position. And there are suppose two electrodes. One is positive electrode and another is negative electrode, which are connected to the myocardium to capture or to record its all electrical activities. What's going on in the myocardium, and it will record it by the galvanometer by showing the deflection towards the positive sides or towards the negative side. Now, as you know that when the heart is in the relaxed condition, or we can say in the rest state, the inside membrane is, or we can say the intracellular environment is more electronegative. So there is a lot of negative ions. There is a lot of negative ions inside the myocardial cells. So the inside, all the cells are in resting state. We can say these are the most electronegative environment inside. So there is no electric charge or electric current will produce, because we have studied that electric current is produced because of the opposite ions, because of the positive and negative ions. And as you know that in relaxed condition there is only negative ions. So this is impossible to produce electrical impulses, or we can say electrical current. Now, when such type of myocardial cells is connected with galvanometer, there will be no deflection. Because there is no charge to detected by the galvanometer. because there is no charge to detect by the galvanometer. Now this is our first observation. Let's draw the second observation. This is suppose second observation. Again, this is what? A in, this is B in, this is positive terminal and this is negative. We can say positive electrodes will attach to this side and negative electrodes will attach to this side, and these both electrodes are attached with the galvanometer. Suppose this is what? This is a galvanometer and this is the needle of the galvanometer. Now we will study the case. Suppose this A end is negative and suppose we touch the A end. We can say there is a stimulus at the A end. So obviously when there is a stimulus, there will be a huge influx of the positive ions, or we can say the sodium ions. And what will happen? The depolarization will start at the A end. The depolarization will start at the A end. So we can say the positive ions, what? The positive ions will flow from A side to what? B side. We can say the positive ions will move from negative side into positive side. So the current direction is from A to B, or we can say the current direction is from the negative terminals to the positive terminal. Always remember 2 points. When the positive charge moving towards the positive terminal, always remember, when the positive charge moving towards the positive terminal or the negative charge moving towards the negative terminal, in both cases deflection will be positive. Deflection will be positive. Suppose this is the positive side of the galvanometer and this is the negative. This is plus 10, plus 20, plus 30. This is minus 10, minus 20, minus 30. Now as you know that the positive charges are moving towards the positive terminal, so obviously reflection will be towards the positive side. Now as the depolarization advancing over the membrane of the myocardium, there will be what? There will be a huge what? Fluctuation, or we can say deflection of the needle, so that as this is from positive towards the positive, so the deflection will be towards the right side. This deflection is toward the right side. This is our second observation. Third observation is, suppose the same myocardial cell, this is B in, positive in, and this is A in, negative in, and both are connected as usual into what? Into galvanometer. This is the needle of the galvanometer, this is positive side and this is negative side. Now is the depolarization advancing, after some time all the myocardium is depolarized. All the myocardium become depolarized, or we can say all the myocardium is filled by the positive charge. As we have already studied that in the first case all the intracellular environment is most electronegative. So because of the one charge, or we can say because of the same charge, there is no action potential. There is no deflection in the needle of the galvanometer. The same is the case. When the myocardium is completely depolarized, there is also the same charge, same positive charge. So there is no electric current. It means there is no action potential. So again, this galvanometer will move from positive side towards its original position 0. So this it will deflect from what? From positive side towards the 0 position. Now this is third observation. Suppose again fourth observation. The same type of myocardial cells. This is B in, positive. This is A in, negative terminal. Again there is what? There is galvanometer. This is the needle of the galvanometer, and these electrodes are attached to the negative side and these are attached to the positive side. Now suppose we stimulate the myocardial cells not on the A side but on the B side. So it means when we stimulate the myocardial cell at point B, what will happen? the myocardial cells is stimulated, it means there will be a huge influx of the sodium ions into the intracellular environment. Or we can say the depolarization will start from the B end towards the A end. So the positive charge, the positive charge, it will move towards what? Toward this side. It will move toward this side. So again, this cell will be depolarized, these cells will be depolarized, and again this depolarization will come into the A. Now, as we have studied that when the positive charge is moving towards the positive terminal, the deflection will always be positive. When the negative charge is moving towards the negative, the deflection will always be negative. But remember, when the positive charge is moving towards the negative terminal, the deflection will always be negative. Remember, when the positive charge is moving towards the negative terminal, the deflection will be negative. This is positive side, this is negative side. So we can say the deflection will be negative. The needle will move to the negative side, or it will show negative deflection. It will show negative deflection. Now, this is another observation. Now, let's take another two types of observation. One is the same like this one. One is the same like this one. And another is, let's take two different types of myocardial cells. One thick myocardial cells and another is thin and thick myocardial cells. Suppose this is thin myocardial cells which is usually present in the atrium. What? Atrium. Always remember, when the current flows from the positive terminal towards the positive or from the positive terminal towards the negative, what will be the direction of the current? The direction of the current will be that in which the charges are moving. Always remember. Now the charges are moving towards the positive side. So, as you know, electric current produce magnetic field. Electric current produce magnetic field. So because of the charge flow, magnetic field will be produced, and magnetic field is because of the magnetic force. So we can say the direction will be represented by a vector. The direction will be represented by what? By vector. This vector, it represents the direction of the flow of the positive charge towards the positive terminal. And the same is the case when the charge moves from the positive terminal towards the negative, the direction of the vector is from B to A. From B to A. Now this is, suppose this is atrial cell, which is thin cell, or we can say there is small number of myocardial cells inside this myocardium. Now we take another myocardium. We take another myocardium which is thick as compared to this one. Now there is a lot of myocardial cells, so the action potential will be larger. As the action potential larger, we can say the deflection will be larger. So the needle will show a huge deflection as compared to the thin myocardium. Now suppose the same type of cell is connected towards the galvanometer. This is B end which is positive and this is A end which is negative. These are connected with what? With a galvanometer. With a galvanometer. This is positive end, this is negative end. Now suppose the same type of cell is stimulated at this side. The same type of myocardium but thicker than this one. So it is stimulated on this side. This is what? Stimulus. So when the stimulus is appropriate, we know that the resting membrane potential will go into the threshold potential, and again there will be a huge influx of the sodium ions. So we can say depolarization will start at this end. What will happen? Depolarization will start at this end, and this depolarization, it will spread into the next cells. So this is what? This is the direction of the current. So we can say this is also the direction of the electromagnetic force. Now this is what? This vector represents the direction of what? Current. Electromagnetic force, or we can say current. Now what is the difference between this thick cell and this thin cell? You can observe the difference. This vector is length is larger. What? Larger length. What is this? This length is longer as compared to this length. This is small length. Small length. Always remember the strength of the electromagnetic force. Always remember the strength of the electromagnetic force depend on the length of the electromagnetic vector, or we can say vector. So this length is smaller as compared to this one, so we can say the strength of the electromagnetic force here will be weak as compared to this one. As compared to this one. Now this is the difference between the thick cells and the thin cells. That how the thin cell will depolarize and what will be the vector. Even the direction is same. Even the direction is same in both cases, but the strength of the electromagnetic force is different because of the size of the myocardium. And this myocardium, as we have already told that this myocardium is present in the atrium because the atrium wall are thinner. So the myocardium will be obviously thinner. And this type of myocardium, which is the thick one, this is present in the ventricles. Present in the ventricles. That is why atrial contraction or atrial action potential is smaller as compared to the ventricle action potential. As compared to ventricle action potential. Now let's study another case, another observation. Suppose the same type of cell is attached with this is A in, B in, positive and negative. This is again attached with what? Galvanometer. With a galvanometer. Now, as we have already studied that, when the cell is stimulated at this point, when the myocardial cell is stimulated at point A, the positive charge will move towards this side. The positive charge will move toward this side, toward the positive. Now, when the myocardium cells is completely depolarization, obviously for complete action potential there will be repolarization. Now the repolarization will start from that end where the depolarization ends. The depolarization ends at that point. Now obviously the repolarization will start from this point. So at this point the repolarization will start, we can say the negative charge. What repolarization means? Negative. Potassium will go out, so the internal environment will become more electronegative. So this negative charge, it will move towards this side. Now as we have already studied that, when the negative charge is moving towards the negative charge, what will be the deflection? The deflection will be positive. When the positive charge is moving toward positive, the deflection will be positive. When the negative charge is moving towards negative, the deflection will be positive. But when the positive charge is moving towards negative, the deflection will be negative. Okay? So negative charge is moving towards negative, the deflection will be positive. And as you know that repolarization start in inverse direction to the depolarization. As you know, the depolarization is in this direction, so obviously the repolarization will be opposite to that of it. So this is repolarization. The direction of the repolarization is opposite to that of depolarization. So vector will be in this direction. So this was actually the electrical observations, which are actually electrical impulses created by myocardium cells, or we can say the SA node, and spread towards the all heart. Now after that we will study that how electrical impulses are produced and how these electrical impulses are translated into vectors and how these vectors are translated into ECG pattern. Now we will study the electrical impulses generated by the nodal cells, or we can say the SA node, and how it's spread into the extremities, or we can say into the ventricles, into the SA node, or into the left atrium. So suppose the heart is in the relaxed condition in which there is no action potential, so we can say that there will be no electrical impulses because the heart is in relaxed state. Now when the heart is stimulated, the SA, or we can say when the SA node fires, so it will produce electrical impulses and it will spread into its atrium, and from this atrium it will move into what? It will move into left atrium. It will move into left atrium and itself into right atrium. As we have already studied that this SA node which generate electrical impulses, it will transfer into the left atrium through the Bachmann bundle, and itself into the right atrium into the internodal pathway. So the direction of the current is down. In this case the direction of the current is down, and in this case the direction of current is towards the left side of the heart, So these two directions are added. Actually, now we will draw the vectors from the electrical impulses from the depolarization spread over the membranes, over the myocardium, and from this depolarization or from this action potential we will draw a vectors, and after that we will convert that vectors into Ecg pattern. So let's draw what vectors. Now these one direction is towards the left and one is downward, so the resultant direction will be towards right and downward. This is the resultant direction of the vector which is produce electrical impulses is produced from the SA node. This is the resultant direction. Okay, after that these, as we have studied that these electrical impulses will transmit from the SA node to what? To AV nodes, or we can say the atrioventricular nodes. Now as you know, the AV node is so small, so it will create electrical impulses, it will transmit electrical impulses, but a very small electrical impulses which are not picked by the ECG machine. We can say the AV node impulses are not picked by the ECG machine, so the heart in this case it will remain silent. And ECG paper, the isoelectric line represent the SA node electrical impulse, which are not picked by what? Which are not picked by the ECG machine. Now after that the electrical impulses will transfer into the bundle of His, and then into the right and left bundle branches, and then into what? Ventricles. Or we can say this depolarization, now it will spread over the myocardium. Now as you know that this septum or this partition is actually fibrous. And fibers are, these are insulators. So the only action potential, it will pass through the AV node into the ventricles. The action potential from the atrium will pass into the ventricles only through the AV node, not through this fibrous structure or fibrous septum. Now when the electrical impulses from the AV node pass into what? Into the septums, into bundle of His, and from bundle of His it goes over the septum, and then from the septum towards the left and right bundle branches, and then from the left and right bundle branches it moves into the ventricles. Now this is a septum, this is interventricular septum, between the left ventricle and between the right ventricle, this is interventricular septum. Now these electrical impulses comes from the SA node into the AV node, and from AV node it will come into the interventricular septum. But the upper part is also fibrous. The upper part is fibrous and the lower part is muscular. So in this is an insulator, so there is no action potential formation in this upper section. In the lower or the basal part, this is muscular, so it is possible to produce action potential. Now as the action potential from the AV node comes, it will first depolarize what? It will first depolarize the left side of the septum, and after that this action potential will spread towards the right side and upward. The action potential will spread toward this side and also upward. So again the direction of the electric current will be added. The direction of the electric current will be added, and the resultant direction is like this one. Like this one. As you know, the SA node will fire, it produces electrical impulses which transmit towards the left side and toward its own atrium. Now these two small directions are added, and this is the resultant vector which is directed towards the right side and downward, and this is directed towards the up and right side, upward and rightward. This is the resultant direction. Now after that, what will happen? The action potential, it will spread into the sides, So we can say the positive charge will move into the sides. The positive charge, it will move into the ventricles, So the direction of A in this case is this one. The direction in this case is this one. You know. And the direction in this case will be this one. It's simple. And after that, these electrical impulses will go towards the, remember, this is the apex of the ventricles. This is the apex of the ventricles. So we can say the apex of the ventricles will depolarize first. And after that, the action potential or the depolarization will go into the base of the ventricles. So this action potential will go and depolarize the base of the ventricle. So this is the direction of the vectors. Now we can say, or we can add these two types of vector because they are in same direction, so they can be added. And again, a large vector is obtained. Large vector is obtained because the direction of the current is actually downward. We can say the depolarization, it will move from the endothelium into the endocardium into the pericardium. Or we can say these near cells, this is called submyocardium endocardium. Submyocardium endocardium, yeah, we can say subendocardium myocardium because it is near to the endocardium, therefore it is called subendocardium myocardium. This side is near to the pericardium, so we can say this is subpericardium myocardium. So the action potential or the depolarization will spread from the submyocardium endocardium, or we can say subendocardium myocardium into the subpericardium myocardium. So this is the direction. This vector which we have already studied, it represents the direction of the current, or we can say the direction of the charge motion. Now let's this is the first vector. How during one complete cardiac cycle, how many vectors will form? This is the first one. There is no vector formation. Because AV node is very small and the electrical impulses are not picked by the ECG machine. So the line will remain straight. We will study after. Then after the AV node, the action potential or the electrical impulses will enter into the interventricular septum, and again when the septum is depolarized, this vector is produced. So this is the second vector. And this is the third vector. Third vector, and this is the fourth, and this is also the fourth vector. Now what will happen? After that, as you know, when the depolarization is complete, repolarization will happen. What will happen? Repolarization will occur. So remember, as we have already studied that depolarization starts from this point. Depolarization will end at this point. Obviously, the positive charge will move towards the Subpericardium, myocardium. Subpericardium, myocardium. So we can say where the depolarization ends, from this point repolarization will start, as we have already studied. When the depolarization moves from the subendocardium myocardium into the subpericardium myocardium, the depolarization started at this point but end at this point. Now repolarization will start from this point and end at this point. What is the reason behind this? Why the repolarization start from the subpericardium myocardium? Now as you know that there are capillaries, there are blood capillaries which are supplied into the pericardium, which are supplied into the endocardium, and which are supplied into the inner cells. These are what? Capillaries. Suppose this is capillary number 1, this is 2 and this is 3. Now when the ventricles contract, suppose ventricle contracts, so it will apply pressure on the inside capillary. It will apply pressure on the inside capillary. As a result, the capillary one will compress. The capillary one will compress, so there will be a small amount, a very small amount of the blood flow through the capillary 1 and large amount of the blood flow through the capillary number 3, which is near to subpericardium myocardium. So the blood through this capillary is larger. As a result, the repolarization will start from this point. As a result, the repolarization will start from this point. As we have already discussed that, we will study the electrical phenomena, electrical impulses, production and spreading, and then after that we will draw vectors, and these vectors will be translated into ECG paper. Now let's draw a simple diagram to represent all the vectors. This is what? This is fibrous band, and this is right atrium, this is left atrium, this is right ventricle, and this is left ventricle. This is what? Left ventricle. Now, what is the first vector? Now we will draw the ECG pattern from the vectors. As we have already studied that in basic concepts of the ECG, we will study the electrical impulses generation, and after that the translation of these electrical impulses into the vectors, and from the vectors we will draw the ECG pattern. So this is actually what? From the electrical impulses, these vectors are produced, and from these vectors now we will draw the ECG pattern. The arrangement is like this. This first arrow, it shows what? The SA node impulses production. This first one and the second one, during which the heart electrical impulses is died, or we can say when the heart is silent, the second one. After that, from the AV node, the impulses will go into the interventricular septum and it will depolarize. This arrow, which is to upward and rightward, it represents the septal depolarization, and after that it will move into the ventricles, and this represents the major ventricle depolarization, or we can say the apical ventricle depolarization. And this is what? This is the base of the ventricles. We can say this is the basal ventricle depolarization. So there are 5 types of vectors. This one is the first vector, second vector, third vector, fourth and fifth vector. Now we will draw the ECG pattern. How is the arrangement? Suppose this is a human heart. This is what? This is a human heart, and into this human heart there attach a galvanometer to record the electrical impulses and to convert these electrical impulses into ECG pattern. So this is what? This is the galvanometer. This is suppose positive end and this is negative end. The positive end is attached into this one and the negative end is attached into this one. Now as you know that, we can say we can attach the ECG leads, the galvanometer leads into this side, into this side and this side. But why? For convenience we attach the ECD leads into one hand and into the left foot for convenience, because the electrical impulses in this point generated by the SA node and at this point is same. Therefore, for simplicity, we put the galvanometer lid into the left foot and the right hand. Now we will draw these vectors into this paper. This is what a special type of ECG paper which is rolled around, which is rolled, and it is attached into a wooden stand, and there is a special type of ECG machine which actually moves the paper, which actually fold the paper or moves the paper to draw the lines, to draw the ECG pattern. And this needle, it touches the ECG paper so that patterns are drawn. Okay. Now, as you know, when the heart is in relaxed condition, there is no electrical impulses, there is no action potential. We can say this line represents when the heart is in a rest state or a relaxing state. Now after that, as you know, when the SA node fire, the action potential will generate. So this vector is actually what? This is because of the sinoatrial node, because of the SA node. Now as you know, this vector is going toward the positive or away from the positive?
Toward.
This is positive. This action potential or depolarization is actually positive charge. So we can say this positive charge is moving toward the positive. The arrow shows direction of the moving of the ions. So this vector is moving toward the positive side.
Yes.
So when the positive moves toward the positive side, the deflection will be
Positive.
Therefore, this deflection is toward the positive side. The deflection is toward the positive side, and such type of wave produced by atrium contraction. Because of the atrium contraction, this is called P waves. Now after that, the electrical impulses go where? It will go into the SA node. And as we know that SA node is small, so the ECG machine will not pick these small electrical impulses. So the heart will be electrically silent. So this straight line, this isoelectric line shows the AV node activity. We can say this is what? This is the AV node activities. Now after that, what will happen when the action potential enter into the septum? It will depolarize the septum. But you know, the direction of the vector is from positive towards the negative. We can say the positive charge is moving towards the negative. So the deflection will be positive or negative? Negative. Obviously negative, but this is a small deflection actually. This is small ventricular deflection. So the deflection will be
small.
Negative. This deflection is actually septum action potential. Now, when this action potential from the septum enter into what? Into ventricle, into major ventricle. What will happen? Major ventricular depolarization will occur. So, what will happen? As you know, this vector is going toward the positive. As you know, this is positive. So from positive to positive, the deflection will be positive. The deflection will be positive, but this is major ventricular depolarization. So there will be a sudden fluctuation in the pattern of ECG. And this, from this point into this point, this is actually what? Major ventricular depolarization. What? Major ventricular depolarization. Major ventricular depolarization.
Qrs waves.
Yes. But this point, this is called P wave. And this is what? Q. This is called R. And this is called
Yes.
S. Now, this isoelectric line, this is called PR segment. This is called PR segment. Now after that, what is the fifth one? This vector is fifth one. Now as you know, this vector, when the basal ventricular depolarization occur, the vector is going away from the positive or towards the positive? Away from the positive is shown. The vector is moving away from the positive towards the negative. So the deflection will be negative. The deflection will be negative, but there a small amount of deflection. A small amount of deflection. Now, what will happen? As you know, when the ventricles are completely depolarized, is there any action potential?
No.
Is there any electrical impulses?
No.
This straight line shows the complete
isoelectric line.
complete ventricular depolarization. Complete depolarization of the ventricle. Now, as you know, when the depolarization complete, obviously the second step is repolarization. So the ventricle will start from what? From the subpericardium myocardium. It will start repolarization. So repolarization start from this point into this. The vector position is
Towards negative.
toward the negative. So we can say positive charge. No. This is repolarization. So negative charge will be greater. We can say this is negative. So the negative moves towards the negative. The deflection will be positive. So this is a positive deflection, but this one is repolarization. Don't be confused this one with this. This is actually P wave when the atrium depolarize, and this is actually when the ventricles repolarize. So from these vector we can draw the Ecg pattern. This is actually normal Ecg pattern. Now we will study that there are how many waves, there are how many segments, there are how many intervals in a normal Ecg. Suppose first we will find waves. Remember, there are 3 waves in a full normal ECG. The first one from this point into this point, this is called P wave. P waves. And the second, from this point from Q to S, this is called QRS wave. QRS wave. Why this is called Qrs complex? Because this is actually a combination of 3 different types of waves. Therefore it is called Qrs complex. Now, the third wave, which is actually what? Because of the repolarization of the ventricle, this is called T waves. So T waves. There are 3 types of waves. One is P waves, one is QRS waves, and another is T waves. Now we will study segments. Number 2, segments in a full normal ECG. The first, there are 2 segments. In normal full ECG. The first segment is these isoelectric lines. What is this isoelectric line? PR segment. Conventionally, we can say PQ segment, but conventionally it is given the name PR segment. So the first one is PR segment, and the second, where is segment? Next segment, or we can say segment is also called isoelectric lines. So where is next isoelectric line? From this point to this, and this is called ST segment. segment. This is called ST segment. Now we will study what? Intervals. We will study intervals. There are three intervals. There are three intervals from what? From this point to this point. From this point, this is actually what? This is actually what? This is PR segment. This is PR segment. Don't be confused PR segment with PR interval. The region from here to here, this is called PR interval. And the region from this point into this point is called PR segment. So actually we can say the PR segment will include only the isoelectric line. But the PR interval will include the isoelectric line as well as the P waves. As well as the P waves. So the first one is what? P R interval. P R interval. The next is from this point into this point. We can say
QRS.
good QRS interval. What? QRS interval. In next is from this Q point into the T. This is called QT interval. This is called QT interval. This is called QT interval. Now let's recap. There are three types of wave in a full complete ECG. One is P type of wave, another is QRS waves, and another is T waves. That's okay. Second is segment. There are two types of segment. One is PR segment and another is T segment. PR segment is from this point into this, and ST segment is from this point into this. We can say the segment is also called isoelectric lines, or we can say the isoelectric line represent the segment of the ECG paper. That's okay. Now intervals. There are three intervals. One is PR interval from this point into this point, which include the isoelectric line as well as the P waves. Another is QRS interval from this point into this point, which include the complete Qrs complex. And another is QT interval from this point into this point. This is called QT interval. Now we will study the time and duration. During which P waves generate, during which intervals are generated, or we can say one complete cycle. In one complete cycle, how much time these P waves will take, how much time this PR segment will take, how much time this Qrs complex will take, and how much time is this ST complex will take. Now we will study the time and duration of the ECG. As we have already studied different types of electrical impulses, and because of these electrical impulses we have drawn different types of vector, and because of these vectors we already draw a normal ECG. Now suppose this is ECG paper, and there are special lines which are particularly made for the ECG. This ECG paper move in this direction. As you know from the previous lecture, this is what? This is the galvanometer attached to the human heart or the human left foot and the right hand. Now it will record the electrical impulses, and these electrical impulses will deflect the needle of the galvanometer and it will draw the ECG pattern. Now there are 300 big square. There are 300 big square in a ECG paper, and we can say there are more than 300 different types of what figures in the ECG paper. But remember, during 1 minute, as you know, the ECG paper will slides over the needle. It will slides over the needle to draw the ECG pattern. So 300 figures, 300 big big figures will pass in 1 minute. In 1 minute, big figures, or we can say what? Big figures will pass in 1 minute. So we can say 300 figures is equal to 60 seconds. 1 minute is equal to 60 seconds. 1 minute is equal to 60 seconds. Now what will happen? This segment, this big segment, this is what? From here to here, this is what? This is one big segment. This is one big segment, and in 1 minute 300 big figure segment, like we use the name of the segment. So in 1 minute 300 segment will pass over the needle in 1 minute. So 1 minute has 60 seconds. We can say 300 segment will pass in 60 seconds. Now one figure, what, or one segment will pass in how much time? This is the question. One segment will pass from the needle in how much time? 60 divided by 300. 60 divided by 300. It is approximately 0.20. 0.20. So we can say one big segment will take a 0.20 second. Now, as you know, remember, in one large segment or in one big segment, there are 5 smaller segments. There are 5 smaller segments. So we can say 5 segments is equal to one big segment. And you know, one big segment take how much time? 0.20 second. 0.20 second. What will happen? One small segment. One SS means one small segment is equal to what? 0.20 divided by 5. To find the time duration during which one small segment pass. 0.20 divided by 5, it is approximately 0.04. It is approximately 0.04 second. 0.04 second. Now, we will study the vectors and we will draw the same Ecg, the same normal Ecg as we have done already. As you know, always remember 3 points. 3 points. The P wave will occupy 2.5 small segment. The P waves will occupy 2.5 what? Small segment. It means this is one small segment, this is 2, this is 2.5. This is 2.5. We can say this is what? P waves? P waves will occupy 2.5 segment. Always remember. And the next PR segment or the PR isoelectric line, it will also occupy the same 2.5 segment. 2.5 segment. And next, the Qrs complex. The Qrs complex, it will also occupy the same 2.5 segment. The same. So this is half, 1, 2. Now what will happen? This is half, 1, 2. So the Qrs will occupy what? Same 2.5 segment. And again, as we have studied the what? PT segment, or we can say QT segment, QT interval. As we have already studied from what? Which also the PR interval from this point into what? Into the repolarization. Into repolarization wave. This is called what? PT interval. PT interval. So the PT interval will occupy 10 small segments. Remember, four major concepts should be remembered. One is P waves occupy 2.5 segment. PR segment P R segment will occupy same 2.5. Qrs complex same 2.5. But the T interval, it will occupy 10 small segment. Remember. Now what will happen? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This one is 10?
Yes.
Sorry. It will occupy now this is actually what? From here to here. This is what? PR segment. PR interval. PR interval. It will occupy how much small segment? 10 small segment. It will occupy 10 small segment. Now we will calculate that P waves take how much time? PR segment take how much time? Qrs complex take how much time? Or we can say PR interval take how much time? Now as you know what? P waves take how much time? P waves occupy 2.5 segment. How much? 2.5 segment. One segment we already calculate. How much second? 0.4. 2.5 means 0.4 plus 0.4 and half means 0.2. 0.2. Now calculate 0.1. We can say the P waves formation takes 0.1 second, as we have already discussed that. The SA node, when generate electrical impulses, it transmit into the AV node in 0.1 second. This is the proof. How in 0.1 second? This is the proof. Okay? PR waves, we can say P waves, it will occupy 2.5 segment. So one segment is 0.4 second. We will add 0.4 second, 0.4 second plus 0.2 second. This is 0.1. Now we will calculate what? PR segment. Again the same. PR segment. How much segment it will occupy? 2.5. The same 2.5. Again 0.4 plus 0.4 plus 0.2. What is this? 0.1. 0.1. Now Qrs complex will take how much time? The same. It occupies the same 2.5. So 0.4 plus 0.4 plus 0.2. The same 0.1 second or 10 second. Now what we will calculate? We will calculate the PR interval. The PR interval. As you know, PR interval occupy how much space? How much segments? 10 small segments. 10 small segments. 10 small segments. One segment take how much time?
0.1.
0.2. Sorry, 0.4. 0.4 second. 0.04 second. This time is taken by one small segment. One small segment take how much time? 0.04 second. 0.04 second. Now 10 small segments will take how much time? 10 multiplied by 0.04. Now this is what? This is how much time? 0.4 second. 0.4 second will take PR interval. Or we can say PR interval will take 0.4 second. So this was actually the major basic concepts of the ECG, and inshallah in next lecture we will study the advanced ECG.